Have you ever gazed up at the night sky and felt that profound sense of wonder, the quiet hum of a universe so vast it defies comprehension? We orbit a star in one galaxy among billions, each containing countless worlds, and yet so much of the cosmos remains shrouded in mystery. How much do we really know about the universe? It's a question that has haunted scientists and dreamers alike for centuries, and today, we're about to dive into answers that might just leave you speechless. Welcome to a journey beyond the familiar, where black holes sing, planets rain diamonds, and time itself behaves in ways that challenge our very understanding of reality. In this video, we're uncovering 30 astonishing facts about space that aren't just mind-bending, they're paradigm-shifting. From the eerie silence of the cosmic void to the violent beauty of dying stars, each revelation peels back another layer of the extraordinary tapestry that makes up our universe. This isn't just a list of trivia. It's an invitation to see the cosmos through new eyes, to question what you thought was possible, and to reconnect with that childlike curiosity that first made you look up and wonder. So buckle up for a cosmic journey like no other. By the time we're done, you won't just have learned something new, you'll have felt the awe and humility that comes from confronting the sublime. These aren't just facts. They're reminders of how strange, beautiful, and shockingly unpredictable the universe truly is. Get ready to have everything you thought you knew about space turned upside down. And it all begins right in our own cosmic backyard with our closest celestial neighbor, the Moon. For centuries, it's been a constant, comforting presence in our sky, the subject of poetry and songs, but it's hiding a secret. The Moon is in a slow, silent retreat, moving away from Earth at a rate of about 1.5 inches every single year. Now, that might not sound like much, roughly the same rate your fingernails grow. But when you multiply that over the immense scale of cosmic time, it adds up to a dramatic reshaping of the Earth-Moon system. This incredible dance is driven by the gravitational tug of war between Earth and the Moon, a phenomenon known as tidal friction. Here's how it works. The Moon's gravity pulls on our planet, and this pull is strongest on the side of Earth facing the Moon. It's this force that creates the ocean's bulges, the high tides we see every day. But Earth is also spinning on its axis incredibly fast, much faster than the Moon is orbiting us. So, our planet's rotation actually drags that tidal bulge slightly ahead of the Moon. That bulge, in turn, exerts its own gravitational pull, which tugs the Moon forward in its orbit, giving it a tiny energy boost. This boost pushes the Moon into a slightly higher, slower orbit, and that's what causes it to drift further away. It's a brilliant, elegant transaction of energy. The Moon gains orbital energy and moves away, and to keep the overall energy in the system balanced, Earth's rotation loses energy, causing our planet's spin to slow down. This means our days are gradually getting longer. Billions of years ago, a day on Earth was only about 18 hours long. In another 200 million years, a day will stretch to 25 hours. And this has profound implications for our distant future. As the Moon continues its retreat, total solar eclipses will eventually become a thing of the past. The Moon will appear smaller and smaller in our sky until it can no longer perfectly cover the Sun. Our tides, the very force driving this change, will also become significantly weaker as the Moon's gravitational influence diminishes. So, the next time you look up at that brilliant full moon, remember, you're witnessing a fleeting moment in a billion-year dance. A partnership that is ever so slowly but surely coming undone. But while our Moon is slowly pulling away, the universe is hard at work mixing a cocktail on a scale we can scarcely imagine. Drifting near the center of our Milky Way galaxy, some 26,000 light-years from Earth, there is a vast molecular cloud known as Sagittarius B2. This isn't just any cloud of gas and dust. It's a sprawling cosmic distillery, and one of its most astonishing ingredients is vinyl alcohol. The sheer quantity is what boggles the mind. Sagittarius B2 contains enough of this complex organic molecule to create not just a few drinks, but literally billions upon billions of liters of the stuff, stretched across a region of space spanning several light years. To put that almost incomprehensible scale into perspective, a single light year is about 6 trillion miles, so we're talking about a cloud of alcohol that would take light itself years to travel from one end to the other. The existence of this cloud is far more significant than just a fun astronomical fact. It's a profound clue in our search for the origins of life itself. The cold, dark vacuum of interstellar space might seem like the last place you'd expect complex chemistry to occur, but that's where the magic happens. On the surfaces of tiny dust grains within these clouds, atoms and simple molecules slowly drift together. Shielded from harsh stellar radiation, they can link up, forming more complex structures like vinyl alcohol, and even the building blocks of sugars and amino acids. It's a quiet, continuous chemistry set operating over millions of years. The discovery of these molecules tells us that the fundamental ingredients for life are not unique to planets. They are being forged in the vastness of space and delivered to new worlds by comets and asteroids. Our own solar system likely formed from a similar molecular cloud, meaning the very chemistry that eventually led to us may have begun in the cold depths between the stars long before our sun even ignited. When astronomers point powerful radio telescopes like the Atacama Large Millimeter Array toward this region, they don't see a visual spectacle of colorful gas. Instead, they detect unique radio signatures, the chemical fingerprints of these molecules as they spin and vibrate in the frigid dark. The data translates into a stunning map of a celestial brewery, a testament to the universe's incredible ability to create complexity from simplicity. So next time you look toward the constellation Sagittarius, know that near the galaxy's heart, there drifts a cloud of alcohol so vast it could serve the entire universe. A reminder that the cosmos is not just a void, but a factory of possibilities. But the universe is full of surprises, and not all of them are cold and distant. For a truly alien weather forecast, we need to travel to our so-called sister planet, Venus. If you thought our neighbor was just a cloudy, hot version of Earth, prepare to have your mind blown. Venus is a world of extremes, a testament to how a runaway greenhouse effect can create a true hellscape. The surface temperature is a constant 870 degrees Fahrenheit, hot enough to melt lead. The atmospheric pressure is 92 times greater than Earth's, equivalent to being nearly 3,000 feet underwater. And if that wasn't enough, its clouds are made of sulfuric acid. In this cauldron of a world, it seems impossible for anything resembling snow to exist. And yet, atop the highest mountains of Venus, there is snow. But this isn't the soft, watery snow we know. This is a snow made of metal. The mountains of Venus, like Maxwell Montes, which is taller than Mount Everest, are capped with a highly reflective, metallic substance. Scientists believe this snow is likely a mix of minerals like pyrite, also known as fool's gold, and other metallic compounds like bismuthinite and galena. Here's the incredible process. Down in the scorching lowlands, these metallic minerals are vaporized by the intense heat, turning into a gas that rises into the slightly cooler atmosphere. As these metallic vapors waft up to the higher, colder elevations of the mountain peaks, they condense directly from a gas into a solid again, a process called sublimation. They then settle on the mountain ridges as a fine, metallic frost. So, it's snow, but it falls from a poisonous sky and is made of fool's gold that settles on peaks under a crushing atmospheric pressure. This entire surreal process was discovered not by any camera, but through the magic of radar. The surface of Venus is perpetually shrouded by those thick, acidic clouds, making it impossible to see the ground with traditional telescopes. Our detailed maps of the planet come from radar-equipped orbiters, like NASA Magellan mission. By bouncing radio waves off the surface and measuring their return, Magellan was able to create stunningly detailed topographic maps. It was these radar maps that revealed the mysterious, highly reflective caps on the tallest mountains, material that behaves unlike the volcanic rock that covers most of the planet. The only logical explanation was a form of precipitation unlike any other in our solar system. This metallic snow doesn't just highlight the utter strangeness of Venus. It shows us how universal physical processes can manifest in wildly different ways depending on the environment. The same basic principle that gives us winter wonderlands on Earth creates a glittering, metallic frost on a world where the very rocks evaporate into the air. It's a powerful reminder that the universe often follows familiar rules, but plays by them in the most spectacularly alien fashion imaginable. Now, if you thought Venus had some bizarre weather, wait until you hear about the mind-bending timekeeping on Mercury. It presents us with one of the most famous paradoxes in our solar system. A day on Mercury is actually longer than its year. At first glance, that statement seems to defy all logic. How can a single rotation take more time than a full trip around the Sun? The answer lies in the peculiar and precarious gravitational dance between the tiny planet and our massive star. To understand this, we first need to define our terms clearly. A year on any planet is the time it takes to complete one full orbit around the Sun. For Mercury, that's a quick 88 Earth days. A day, however, is the time it takes for the planet to complete a single rotation on its axis, which is how we define the period from one sunrise to the next. This is where Mercury gets weird. It rotates on its axis incredibly slowly, taking 59 Earth days to spin around just once. So, its rotation period is 59 days, and its orbital period is 88 days. The year is still shorter, so where does the idea of a longer day come from? The key is in that sunrise to sunrise measurement. Because Mercury is both rotating and orbiting at the same time, the motion of the Sun across its sky is a bizarre spectacle. Imagine standing on the surface of Mercury. The Sun would appear to rise incredibly slowly, inching its way across the black sky. But as the planet moves along its elongated, egg-shaped orbit, its speed changes drastically. At its closest point to the Sun, Mercury moves much faster in its orbit. For a brief period, this orbital speed actually outpaces the planet's glacial rotational spin. From the perspective of someone on the surface, this causes the Sun to stop its crawl across the sky, reverse direction for a short time, and then resume its path toward the horizon before finally setting. This entire drawn-out process, from one sunrise to the next, takes a staggering 176 Earth days. That's exactly 2 Mercury years. So, a single solar day on Mercury. The time between 2 noons is twice as long as its year. This unusual relationship is not a random coincidence. It's a stable configuration known as a spin-orbit resonance, specifically a 3-to-2 resonance. For every 2 orbits Mercury makes around the Sun, it completes exactly 3 full rotations on its axis. This resonance is a direct result of the Sun's immense gravitational pull on the planet. Over billions of years, tidal forces have gently tugged and slowed Mercury's spin until it became locked into this stable, rhythmic pattern. This gravitational locking is what gives the planet its extreme environment. The long day means one side of the planet is baked for Earth months under the relentless, close-range Sun, heating the surface to 800 degrees Fahrenheit, hot enough to melt zinc. Meanwhile, the night side, deprived of sunlight for an equally long period, plunges to nearly 300 degrees below zero. Mercury is a world of ultimate extremes, a testament to how the simple, predictable laws of orbital mechanics can combine to create a clockwork of profound and beautiful strangeness. If the slow-motion day on Mercury feels like a temporal oddity, the universe has a way of turning the bizarre into the truly spectacular. Far beyond our solar system, about 40 light-years away in the constellation Cancer, orbits a world of unimaginable wealth and fury. Astronomers call it 55 Cancri E. but it's earned a far more captivating nickname, the Diamond Planet. This isn't a poetic metaphor or science fiction. It's a super-Earth whose very composition is likely a glittering testament to cosmic alchemy. The story of this incredible world begins with its star, 55 Cancri A, which is part of a binary star system. This star has one crucial characteristic that set the stage for planetary creation. It possesses a much higher ratio of carbon to oxygen than our own Sun. When the planetary disk coalesced around this star, it was therefore rich in carbon, the same element that forms the basis of diamonds, graphite, and life here on Earth. Under the right conditions of immense pressure and heat, carbon atoms can bond in a tetrahedral lattice structure, creating diamond, and 55 Cancri E provides those conditions in spades. This exoplanet is classified as a super-Earth due to its size. It's about twice the width of our own planet, but possesses a mass nearly 8 times greater. This tells scientists that it is incredibly dense. Its proximity to its host star is the final, crucial piece of the puzzle. It orbits 25 times closer to its star than Mercury does to our Sun, completing a full revolution in just 18 hours. This blistering proximity locks the planet in a scorching embrace, heating its surface to a staggering 2,700 degrees Celsius. That's hot enough to melt iron and even platinum with ease. Now, imagine the interior of this world. Scientists theorize that at least a third of the planet's mass, that's a quantity of diamond roughly 3 times the mass of Earth, could be crystallized carbon. The immense gravitational pressure from its great mass, combined with the searing internal heat, creates the perfect natural forge. Deep beneath a surface that might be a turbulent ocean of superheated lava, the carbon is compressed into a solid crystalline structure, forming a mantle of diamond. Some models even suggest the planet could have a sparkling diamond crust, with graphite mountains potentially rising above seas of molten silicon. Picturing this world is an exercise in embracing extremes. Artistic renderings based on scientific data depict a dark, rugged world that shimmers with a faint, internal glitter under the hellish red glow of its enormous parent star. There would be no solid surface as we know it. The landscape might be a constantly churning, incandescent sludge, too hot for any known material to remain solid for long. Any prospector hoping to mine this world would be instantly vaporized, their dreams of riches disappearing in a cloud of plasma. The Diamond Planet stands as a breathtaking example of how diverse planetary formation can be. It's a world forged from the ashes of stars, crystallized by pressure, and illuminated by the fires of its sun, a glittering jewel in the cosmos, beautiful and utterly unreachable. But the stunning, glittering fury of a diamond planet is something we can only observe from a phenomenal distance. To truly experience the cosmos, we have to consider not just what's out there, but how we would perceive it with our own senses. And this leads us to one of the most profound and counterintuitive truths about the universe. Space is utterly, completely silent. If you were to find yourself floating in the void between stars, the experience would be one of absolute quiet, a silence so deep it would be unnerving. This isn't just a lack of noise, it's a fundamental property of the universe itself, dictated by the very nature of sound. Sound, as we understand it, is a mechanical wave. For it to travel, it needs a medium, a substance made of molecules that can vibrate and bump into each other, transferring energy in a chain reaction from a source to our ears. Here on Earth, that medium is our atmosphere. A crashing wave, a roaring engine, the words we speak. All of these create vibrations in the air that our eardrums interpret as sound. But space is a vacuum. It is, for all intents and purposes, empty. The particles of gas and dust are so incredibly sparse that they are, on average, meters apart. There is no air, no water, no continuous medium for those molecular vibrations to occur. A star could explode just a few hundred kilometers away, and you would hear absolutely nothing. The colossal, unimaginable energy of a supernova would release a cataclysm of light and radiation, but its thunderous roar would be silenced by the void. So how do astronauts aboard the International Space Station communicate? They rely entirely on radio waves, which are a form of electromagnetic radiation, just like visible light. Unlike sound, electromagnetic waves do not need a medium to travel. They can propagate perfectly through the emptiness of space. An astronaut's microphone picks up the vibrations of their voice, converts them into an electrical signal, and then that signal is superimposed onto a radio wave and beamed to another astronaut's headset or to mission control on Earth. The receiver then translates the radio signal back into vibrations, recreating the sound inside the helmet. The conversation is happening, but it's happening inside their suits. The space around them remains perfectly, eerily quiet. Astronauts who have conducted spacewalks often describe this silence as one of the most overwhelming aspects of the experience. They are working in an environment of intense visual drama, with the brilliant, sunlit Earth scrolling by below them against the infinite blackness of space. Yet, their only auditory companion is the sound of their own breathing and the hum of their life support system inside the helmet. There is no wind, no rustling, no distant hum of machinery, just the profound stillness of the cosmos. This stark reality is something that science fiction movies almost always get wrong for the sake of drama. The iconic roar of TIE fighters screaming past an X-wing, the deep thrum of a starship's engines, the explosive thump of a laser cannon hitting its target. These are all fantastic additions that make for a thrilling cinematic experience, but they are physically impossible in the true vacuum of space. The universe may be filled with violent, energetic events, but it conducts its business in the most deafening silence imaginable, a quiet that underscores both the grandeur and the indifference of the cosmos to our presence. This deep, cosmic silence that surrounds every celestial object is also the very reason some of humanity's most fragile marks have been preserved for eons. Those iconic footprints left by the Apollo astronauts on the lunar surface aren't just a moment frozen in time for history books. They are a geological record destined to outlast nearly every human monument on Earth. While wind and rain would have erased them in a matter of months on our planet, on the Moon, they could remain perfectly preserved for millions of years. This incredible longevity is a direct result of the Moon's profound lack of a dynamic environment. Our active Earth is a world of constant change, sculpted by the forces of erosion. Our atmosphere acts as a relentless engine of weathering, with wind scouring surfaces and redistributing dust. Water cycles through rain, rivers, and ice, dissolving and reshaping the landscape. Even tectonic activity slowly recycles the very crust we walk on. The Moon has none of this. It is a fossil world, geologically dead for billions of years. There is no air, no wind, no flowing water to gently wash away impressions in the soil. The lunar regolith, the layer of fine, dusty soil that covers the Moon's surface, was compressed by the astronauts' boots into a distinct, cohesive layer. In the complete absence of any weather, those footprints are essentially locked in place, vulnerable only to the incredibly slow and random processes of the space environment. So what will eventually erase these historic marks? The primary force is a slow, patient sandblasting from micrometeorites. The Moon has no protective atmosphere to burn up the constant rain of tiny space dust particles that hurtle through the solar system. These microscopic projectiles, some no larger than a grain of sand, strike the lunar surface at tremendous speeds. Over millions of years, this relentless, microscopic bombardment will very gradually churn the top layer of the regolith in a process scientists call impact gardening. It's an incredibly slow-motion erosion, where each tiny impact kicks up a minuscule amount of dust that eventually settles back down, subtly smoothing and mixing the surface over immense timescales. It's a process so gradual that the flag planted at Tranquility Base won't be toppled by a storm. but will instead be slowly and uniformly faded by a drizzle of space dust over millennia. The remarkable preservation on the Moon offers a stunning side-by-side comparison. High-resolution images from NASA, a lunar reconnaissance orbiter, have captured the Apollo landing sites as they appear today. When we compare these modern images with the photos taken by the astronauts themselves half a century ago, the changes are virtually non-existent. The descent stages of the lunar modules sit exactly where they were left. The paths of the lunar rovers are still clearly visible as darker tracks against the gray soil. And yes, the footprints themselves remain sharp and well-defined. This isn't just a trivial observation. It provides planetary scientists with crucial data. It confirms our understanding of erosion rates on airless bodies and tells us that any features we see on similar worlds like Mercury or asteroids could be astonishingly ancient. The footprints are more than a symbol of human achievement. They are a permanent experiment, a time capsule placed on the lunar surface that will silently teach future generations about both our ambition and the incredible stillness of the world we briefly visited. Yet the enduring silence of the Moon is a mere whisper compared to the profound emptiness that defines some regions of the cosmos itself. Imagine a sphere of nothingness so vast that it could swallow thousands of galaxies like our own, yet inside, you would find almost nothing. This isn't a theoretical concept. It's a real, cavernous hole in the fabric of the universe known as the Boötes void. Discovered in the early 1980s by astronomers Robert Kirshner and his team, this colossal region of space stretches an almost incomprehensible 330 million light-years across. To grasp that scale, consider that our entire Milky Way galaxy is a mere 100,000 light-years from end to end. You could line up over 3,000 Milky Ways side by side, and they would still fit within this expanse of near-total emptiness. When it was first mapped, the Boötes void, sometimes dramatically called the Great Nothing, presented a monumental problem for cosmologists. Our prevailing models of the universe's large-scale structure were based on the concept of the cosmic web, a vast, interconnected network of galaxy clusters and superclusters separated by great, bubble-like voids. These voids are a normal part of the universe's architecture, but the Boötes void was an extreme outlier. It was far, far emptier and enormously larger than any void predicted by theory. Initial surveys found only a handful of galaxies in that entire volume of space, where scientists would have expected to find many thousands. It was as if someone had taken a giant cosmic cookie cutter and removed a gigantic piece of the universe, leaving behind a stunningly blank spot on the map. This discovery forced a major revision in our understanding of how the universe evolved after the Big Bang. The current leading theory suggests that such immense voids are the result of gravitational dynamics operating on the very largest scales. In the early universe, matter was not distributed perfectly evenly. There were tiny, random fluctuations in density. Over billions of years, gravity amplified these small differences. Regions that were slightly denser than average pulled in more and more matter, eventually forming the great walls and filaments of the cosmic web. Conversely, regions that were slightly less dense lost matter to their greedier neighbors, becoming ever more empty. The Boötes void is likely one of these underdense regions that grew to an epic scale, a gravitational echo from the very beginning of time. Modern, more sensitive telescopes have since found a few more galaxies drifting in this great emptiness, bringing the total to around 60. But this is still a number so vanishingly small that the void remains a place of profound isolation. If our own Milky Way resided at the center of the Boötes void instead of in a relatively crowded filament, our night sky would be almost entirely black. Without the light of nearby galaxies, the astronomer Edwin Hubble would never have discovered the expansion of the universe. We might have gazed up at a void so empty that we would have had no clue that other galaxies even existed, potentially forever altering our understanding of our place in the cosmos. The Boötes void stands as a humbling reminder that the universe is not just full of wondrous things, but also defined by the majestic. awe-inspiring spaces in between. But the vast, empty expanse of the Boötes void represents a profound stillness on the grandest of scales, a quiet that is broken in the most spectacular way by some of the universe's most dynamic and dense objects. If you want to witness the ultimate expression of cosmic spin, you need to look at the remains of a giant. When a massive star ends its life in a supernova explosion, its core collapses under its own immense gravity. What's left behind is a neutron star, a city-sized object so incredibly dense that a single teaspoon of its material would weigh billions of tons on Earth. And many of these stellar corpses are spinning at a rate that defies all earthly intuition, some completing hundreds of full rotations every single second. This mind-boggling rotational speed is a direct and beautiful consequence of one of the most fundamental laws of physics, the conservation of angular momentum. It's the same principle that explains why an ice skater spins faster when they pull their arms in tight to their body. The skater starts a slow spin with their arms outstretched. As they pull their arms in, they are concentrating their mass closer to their axis of rotation. Because their angular momentum must remain constant, their rotational speed has to increase dramatically to compensate. Now imagine that on a stellar scale. A giant star, much larger than our Sun, might be rotating relatively slowly, perhaps once every few weeks. But when it explodes, its outer layers are blasted away into space, and its core collapses from a sphere hundreds of thousands of miles wide down to a ball barely 12 miles across. This is an unimaginable contraction. The star's mass is suddenly concentrated into a volume over 1 trillion times smaller. To conserve its original angular momentum, the neutron star's rotation must accelerate to an incredible degree. A slow, stately spin transforms into a dizzying, ultrafast whirl, with some neutron stars rotating over 700 times per second. At that speed, the surface at the equator is moving at a significant fraction of the speed of light. This rapid rotation, combined with an incredibly powerful magnetic field, gives rise to one of astronomy's most useful and fascinating phenomena, the pulsar. A pulsar is essentially a rotating neutron star that we observe from a specific angle. The neutron star's magnetic poles are not aligned with its rotational poles. As it spins, beams of intense radiation, radio waves, X-rays, and more shoot out from its magnetic poles like the beams from a cosmic lighthouse. If Earth happens to lie in the path of one of these sweeping beams, our telescopes detect a very regular, rapid pulse of energy with each rotation. The timing of these pulses is astonishingly precise, rivaling the accuracy of atomic clocks. For decades, astronomers have used these predictable signals as cosmic navigation tools and laboratories for testing the laws of physics under extreme conditions. To truly appreciate the character of these objects, you can listen to them. Because their signals are so regular, scientists can translate the radio pulse frequencies into sound waves within the range of human hearing. The result is not a continuous sound, but a series of distinct, rhythmic clicks. Some sound like a steady, rapid heartbeat, a sharp tick-tick-tick that speaks to the incredible clockwork precision of the universe. Others have more complex patterns, especially in binary systems where the neutron star is feeding on a companion star, creating a faster, more frantic, pulsing sound. These audio representations transform abstract data into something visceral, allowing us to hear the steady, rapid beat of a city-sized object spinning faster than a kitchen blender, a haunting reminder of the violent death and incredible rebirth that created it. The pulsar's relentless signal is a testament to the fact that even in the cold vacuum of space, the universe is alive with rhythm and motion on a scale we are only beginning to understand. And from the bizarrely empty to the incredibly dense, we've seen how space constantly defies our expectations, but one of its most common surprises is hiding in plain sight. We tend to think of Earth as the water world, a rare blue marble in a vast, dry desert. The reality, however, is that water is one of the most abundant molecules in the entire universe. It's out there in staggering quantities, but it exists in forms and places that would seem utterly alien to us. The journey of a water molecule in space begins in the cold, dark nurseries of stars. Those same vast molecular clouds we discussed earlier, like Sagittarius B2. Deep within these clouds, where temperatures hover just a few degrees above absolute zero, oxygen atoms, which were forged in the hearts of long-dead stars, drift slowly and stick to the surfaces of tiny dust grains. When hydrogen atoms, the most common element in the universe, bump into these dust-covered oxygen atoms, a reaction occurs, forming a molecule of water ice. This is how, molecule by molecule, vast reservoirs of water are built up over millions of years. Later, when shockwaves from a nearby supernova or the gravitational pull of a forming star stirs up these clouds, the ice-coated dust grains can clump together, eventually becoming part of new planetary systems. This means the water in your glass right now, and the water that makes up most of your body, likely began its journey as ice on a speck of dust in one of these ancient cosmic clouds. The forms this cosmic water takes are as varied as their locations. We've found it in the atmospheres of gas giants, as vapor spewing from the geysers of icy moons like Saturn's Enceladus, and even as vast, diffuse clouds of steam surrounding infant stars. Perhaps the most surprising reservoirs are the ones in our own solar system. On Mercury, the planet closest to the Sun, radar imaging has revealed patches of water ice hiding in the permanent shadows of deep polar craters, where the fierce solar heat never reaches. Similarly, on our own moon, probes have confirmed the presence of water ice in the same kind of eternally dark craters at the lunar poles. This discovery completely overturned the long-held belief that the moon was bone dry. The key to finding this water across such immense distances isn't with cameras, but with spectroscopy. When light from a distant star passes through a planet's atmosphere or a cloud of material in space, the molecules within that cloud absorb specific, unique wavelengths of light. Water vapor has a very distinct absorption fingerprint. By using powerful telescopes to break apart the light from these distant objects into a spectrum, a rainbow of colors, scientists can look for the telltale dark lines where water has absorbed that light. It's like taking a chemical fingerprint of the cosmos from light years away. This is how we've detected the steam-filled atmospheres of exoplanets and the spectral signature of water in galaxies billions of light years from Earth. The implications of this are monumental, especially for the search for life beyond our world. Water is the universal solvent essential for the chemistry of life as we know it. Finding it so plentifully available throughout the galaxy dramatically increases the number of potential habitats for alien biology. It means that moons like Europa and Enceladus, with their subsurface salty oceans, are prime candidates in our search. Furthermore, for future human exploration, locating these off-world water sources is the key to sustainable presence in space. Water isn't just for drinking. It can be split into hydrogen and oxygen for rocket fuel and breathable air, turning a distant moon or asteroid into a cosmic gas station. So the next time you see a rainbow or take a sip of water, remember that you're experiencing a small piece of a universal phenomenon, a substance that connects our world to the farthest reaches of the cosmos, making the universe feel just a little bit more like home. While the vacuum of space ensures an eternal silence for any human listener, that doesn't mean the objects within it are quiet. In fact, our own sun is a massive, churning ball of plasma that is constantly vibrating, creating a powerful, deep hum. We can't hear it directly, of course, because sound waves cannot travel through the void. But if we could, the sound would be a continuous, low-frequency drone resonating across the solar system. This phenomenon isn't just a curiosity. It's the entire basis for the field of heliosismology, which allows scientists to literally listen to the interior of a star. The process begins with the sun's incredibly dynamic surface, The convection zone, a massive layer of churning plasma that makes up the outer third of the Sun, acts like a colossal engine for generating sound. Here, massive cells of hot gas constantly rise to the surface, release their heat, and then plunge back down into the interior. This turbulent motion is like a continuous, planet-sized earthquake, generating powerful pressure waves, acoustic waves, that ripple through the solar interior. These waves bounce around inside the Sun, reflecting off its surface and traveling through its core. By carefully observing the Sun's surface with incredibly precise instruments on satellites like the Solar and Heliospheric Observatory, scientists can detect these ripples. They measure the Doppler shift, the tiny changes in the light waves as the solar surface moves in and out, pulsating from these internal waves. It's akin to watching the entire surface of the Sun breathe in and out ever so slightly. This data, which is a record of the Sun's surface movements, is then translated into sound through a process called sonification. Scientists take the frequencies of these vibrations and mathematically shift them up by a massive factor, bringing them into the range of human hearing. What emerges is not a random noise, but an eerie, deep, and resonant drone. It sounds like a low, primordial hum or the deep tone of a massive Buddhist singing bowl, a sound that seems to carry the weight and age of the star itself. These sonifications are more than just spooky space music. They are a direct audio representation of the Sun's internal structure. By studying the precise frequencies and patterns of these sounds, heliosseismologists can perform a detailed analysis of the Sun's interior, much like geologists use seismic waves from earthquakes to map Earth's inner layers. Different frequencies penetrate to different depths, and by analyzing how these waves travel and change, scientists can infer the Sun's internal temperature, density, rotation, and composition. This is how we know the Sun rotates differently at its equator than at its poles, and how we can detect massive rivers of plasma flowing beneath the surface. This deep understanding is also critically important for predicting space weather. The same dynamics that generate these acoustic waves also drive solar flares and coronal mass ejections, explosions of radiation and particles that, when directed at Earth, can disrupt satellites, power grids, and communications. By listening to the Sun's vibrations, we gain a crucial early warning system for these potentially damaging storms, turning the star's own deep song into a tool for protecting our technological civilization. While our solar system seems like a tidy model of planets neatly orbiting a central star, this is not the only way a world can exist. In the deep, dark stretches between the stars, there are entire planets adrift, untethered to any sun. These are rogue planets, and they are some of the most lonely and enigmatic objects in the entire galaxy. Picture a world wandering in perpetual night, a frozen globe drifting through the interstellar void with no sunrise to warm its surface and no other planets for company. It is a profoundly different existence from anything in our own cosmic neighborhood. The existence of these solitary wanderers forces us to reconsider how planetary systems are born and evolve. Astronomers believe most rogue planets form in one of two ways. The first is the more dramatic ejection model. In the chaotic early days of a young star system, the gravitational dance between newly formed protoplanets is violent and unstable. As large gas giants jostle for position, their immense gravity can slingshot smaller, Earth-sized planets out of the system entirely, casting them adrift into the galactic wilderness. The second, and perhaps more common, method is that they form on their own. Instead of coalescing from a disk of material around a star, a small, dense knot within an interstellar gas cloud could collapse under its own gravity to form a planet-sized object directly, never having a parent star to begin with. These would be cold, dark worlds from their very inception. Finding these dark wanderers is one of the greatest challenges in modern astronomy. Without a star to illuminate them, they are virtually invisible to traditional telescopes. So how do we detect them? The primary method is a phenomenon called gravitational microlensing. When a rogue planet drifts precisely between Earth and a distant background star, its gravity acts like a tiny lens, bending and focusing the light from that star. For a brief period, from a few hours to a couple of days, the background star appears to temporarily brighten. The specific characteristics of this brightening event, its duration, symmetry, and intensity, tell astronomers the mass of the object causing it, confirming the presence of a planet and providing an estimate of its size. It's a difficult and rare observation, like spotting a single floating pinhead in an ocean by the way it magnifies a specific grain of sand on a distant shore. But it has proven remarkably effective. The conditions on such a world would be unlike anything we can easily imagine. With no external source of heat, the surface temperature would hover just a few degrees above absolute zero, plunging into a deep and permanent freeze. The landscape would be a frozen wasteland, likely composed of ices of nitrogen, methane, and water, as hard as rock. The sky above would be perpetually black, punctuated not by a sun, but by the unmoving, brilliant tapestry of the Milky Way and its distant stars. There would be no day-night cycle, no seasons, and likely no weather beyond the slow sublimation of ices in the minuscule heat generated from the planet's radioactive core. Yet, this does not automatically rule out the possibility of life. If a rogue planet retained a thick hydrogen atmosphere, it could trap enough internal geothermal heat to maintain a vast, subsurface ocean of liquid water beneath a frozen crust, much like Jupiter's moon Europa. In such a dark, pressurized abyss, life could potentially arise around hydrothermal vents, sustained entirely by chemical energy rather than sunlight. These lonely worlds, once thought to be barren deserts, might actually be some of the most common harbors for life in the galaxy, hidden in the deep freeze between the stars. But for all the silent, frozen worlds drifting in the dark, our solar system has its own dynamic spectacle of change, one that is slowly fading from view. For centuries, astronomers gazing at Jupiter through their telescopes have been captivated by a massive, swirling crimson eye staring back from the gas giant's cloud tops. This is the Great Red Spot, a storm so vast that it could once comfortably swallow 2 or 3 Earths side by side. It's the largest and most powerful anticyclonic storm in the solar system, a hurricane that has raged for at least 190 years, and possibly as long as 350. But this iconic feature, a permanent-seeming landmark on the face of Jupiter, is undergoing a profound transformation. It is steadily, undeniably shrinking. Our historical records paint a clear picture of this gradual diminishment. When astronomers like Giovanni Cassini first described a permanent spot on Jupiter in the mid-1700s, their sketches and notes suggest it may have been even larger than the storm we know today. Detailed observations throughout the 19th and 20th centuries, especially with the advent of photography, began to track its slow retreat. But it was the era of space exploration that gave us the most precise data. When the Voyager probes flew past Jupiter in 1979, they measured the Great Red Spot at over 23,000 kilometers across, wide enough to fit 2 Earths with room to spare. By the time the Hubble Space Telescope began its regular monitoring of the outer solar system, that measurement had dropped significantly. Recent observations show the storm is now just under 16,000 kilometers across, barely large enough to hold a single Earth. Time-lapse animations compiled from decades of Hubble and ground-based telescope images show this process in stark clarity. The once oval storm appears to be contracting into a more circular shape, and its iconic brick red color has been intensifying as it shrinks. The atmospheric dynamics behind this change are complex and tied to the very nature of Jupiter's chaotic weather layer. The Great Red Spot is essentially a massive high-pressure system, an island of stability surrounded by raging jet streams that tear across the planet. It's not a storm in the sense of a terrestrial hurricane that draws energy from warm ocean water. Instead, it's powered by the internal heat of Jupiter itself radiating upward, interacting with the complex chemistry and physics of the upper atmosphere. The prevailing theory for its shrinkage involves intricate interactions with smaller storms and the jet streams themselves. As these chaotic atmospheric features buffet the edges of the Great Red Spot, they essentially act like a kind of atmospheric sandpaper, eroding the storm and peeling away ribbons and swirls of its outer layers. The storm is constantly consuming smaller vortices that get too close, but the net effect over recent decades has been a loss of overall mass and energy. What does this mean for the future of Jupiter's weather? The short answer is that planetary scientists aren't entirely sure. Some models suggest the shrinkage could eventually stabilize, and the storm might persist for many more decades, perhaps even centuries, as a smaller but still powerful feature. Other, more dramatic hypotheses suggest that the weakening of the storm could lead to its eventual dissolution within our lifetimes. If the Great Red Spot were to vanish, it would fundamentally alter the appearance of our solar system's largest planet and remove a key laboratory for studying atmospheric physics. For centuries, it has served as a natural experiment, allowing us to understand how massive, long-lived weather systems behave. Its powerful winds, which whip around its edges at speeds exceeding 400 miles per hour, and the mysteries of its unique chemistry that produces its deep red color, are all active areas of research. Watching it change in real time offers a rare opportunity to witness planetary evolution on a human timescale. A reminder that even the giants of our solar system are not static monuments, but dynamic, ever-changing worlds. Yet for all its profound silence, the cosmos is not without a scent. After spacewalks outside the International Space Station, astronauts returning to the airlock and removing their helmets are greeted by a very distinct and unexpected odor clinging to their suits. It's a smell they've consistently described as a mix of seared steak, hot metal, and welding fumes, with some also noting a sharp, acidic quality reminiscent of ozone or gunpowder. This isn't the smell of space itself. As a vacuum, it has no aroma to breathe, but rather the smell of space on something, a scent released when compounds that have adhered to the suit during the extravehicular activity are brought back inside and exposed to the station's oxygen-rich atmosphere. So where does this metallic, charred aroma actually come from? The source is as cosmic as it is fascinating. The scent is believed to be caused by polycyclic aromatic hydrocarbons, or PA. These are complex, hardy molecules made of linked rings of carbon and hydrogen atoms, and they are among the most abundant carbon-based compounds in the entire universe. They are formed in the fiery final moments of dying stars, forged in the immense heat and pressure of stellar explosions. From there, these molecules are blasted across interstellar space, eventually becoming incorporated into vast molecular clouds, the very nurseries where new stars and planets are born. When astronauts venture outside, their spacesuits act like a kind of cosmic scratch and sniff sticker, collecting these tiny particles that are drifting through the void. The process of smelling it is a unique ritual of space travel. During a spacewalk, the suit is exposed to the raw vacuum. The high-energy radiation from the sun, known as solar wind, bombards the suit's surfaces and any particles stuck to it, altering their chemistry. Upon repressurization in the airlock, these now activated compounds essentially off gas, releasing their scent into the breathable air for the first time. It's a direct, tangible connection to the most energetic processes in the galaxy, a scent literally distilled from the death of stars and the birth of new solar systems. Astronauts like Don Pettit have poetically described it as a sweet metallic smell, while others like Thomas Jones have noted it was acrid and distinctive. This shared sensory experience across different missions and astronauts confirms it's a real phenomenon, not just an isolated observation. This olfactory signature is more than just a curious anecdote. It provides a profound, human-scale connection to the grand cosmic cycle. The same class of molecules that creates the scent of space on a suit is also found right here on Earth in things like barbecue grills, automobile exhaust, and burnt toast. More significantly, PAHs are considered one of the fundamental building blocks of life, as they can readily form more complex organic molecules under the right conditions. So when an astronaut catches that whiff of seared steak, they are inhaling a reminder that the ingredients for life are not confined to our planet. They are everywhere, a fragrant testament to our deep and literal connection to the universe, written not in light or sound, but in a scent that lingers on the suit of an explorer returning from the void. But the universe is never short on patterns that defy our expectations, and one of the most stunningly geometric exists not on a frozen moon or a drifting rock, but wrapped around the North Pole of a gas giant. While Jupiter's great red spot is a swirling vortex, Saturn presents us with a feature of such perfect geometry it looks almost artificial: a colossal, six-sided hexagon encircling its North Pole. This isn't a mere cloud formation. It's a persistent jet stream, a six-sided wave of winds raging at incredible speeds, and it's a phenomenon unlike anything else we've observed in our solar system. The scale of this atmospheric marvel is almost impossible to comprehend. Each side of the hexagon is longer than the diameter of Earth. The entire structure is so vast that you could line up 4 of our planets side by side, and they would still fit snugly within its boundaries. For decades, we had no idea it even existed because it was shrouded in the long polar night of Saturn's winter. It was finally revealed in all its glory by the Voyager spacecraft in the 1980s, but it was NASA Cassini mission, which orbited Saturn for 13 years, that gave us our most breathtaking and detailed views. Cassini's cameras captured the hexagon in incredible detail, showing it as a deep, creamy yellow band, with a massive hurricane-like storm spinning directly at its center. Time-lapse videos created from Cassini's imagery show clouds whipping around the hexagonal path as if on a racetrack, their motion proving this is a dynamic, wind-driven feature. The million-dollar question, of course, is how does a perfect geometric shape form naturally in a planet's atmosphere? The prevailing theory points to the deep layer dynamics of Saturn's gaseous interior. Scientists believe it's created by what's known as a steep latitudinal gradient in the speed of the atmospheric winds. In simpler terms, as you move north or south on Saturn, the speed of the east-west jet streams changes very rapidly. This creates a kind of atmospheric shear, and under the right conditions, this shear can generate massive, stable standing waves. Think of it like the different notes you can produce by vibrating a guitar string. The hexagon is essentially a persistent planetary scale wave, pinned in place by Saturn's rotation. Laboratory experiments here on Earth have even recreated similar polygonal shapes by spinning a fluid at different speeds in a circular tank, lending strong support to this fascinating theory. It's natural to compare it to Earth's own polar vortex, but the differences are profound. Our polar vortices are large regions of cold, swirling air, but they are transient, often breaking down and reforming, and they are far more circular and less defined. Saturn's hexagon, by contrast, has remained stable and strikingly geometric for decades, possibly even centuries, a testament to the vastly different and more powerful atmospheric forces at work on a gas giant. This incredible structure is more than just a celestial curiosity. It's a natural laboratory. By studying it, planetary scientists can learn fundamental truths about how fluids and gases behave under extreme conditions, offering insights that apply to atmospheric physics everywhere. It stands as a majestic reminder that the universe, for all its chaotic beauty, also operates with a hidden and precise mathematical order, etching a perfect hexagon onto the face of a distant world. But as we marvel at the visible structure of a hexagon on Saturn or the swirling storms of Jupiter, we are only seeing the barest surface of reality. The stunning truth is that every galaxy, star, and planet we can observe with our most powerful telescopes accounts for less than 5% of the entire universe. The remaining 95% is composed of two mysterious, invisible components that we can neither see nor directly touch: dark matter and dark energy. This isn't a small gap in our knowledge. It's a humbling chasm, a reminder that the cosmos we perceive is just the faintest glitter on the surface of a deep, dark ocean whose true nature remains almost entirely hidden from us. We first stumbled upon the evidence for dark matter back in the 1930s through the work of astronomer Fritz Zwicky. He was studying the Coma cluster, a massive group of galaxies, and noticed something bizarre. The individual galaxies within the cluster were moving so quickly that the visible mass of all the stars and gas he could see was nowhere near enough gravity to hold the cluster together. It should have flown apart long ago. He concluded that there must be some unseen dunkel materie, or dark matter, providing the extra gravitational glue. But it wasn't until the 1970s, with the work of Vera Rubin on the rotation of individual galaxies, that the evidence became undeniable. Rubin found that stars at the outer edges of spiral galaxies were orbiting just as fast as those near the center. According to the laws of gravity, these outer stars should be moving much more slowly unless there was a huge amount of invisible mass surrounding the galaxy, its gravity whipping the stars around like a merry-go-round. So how do we study something we can't see? We observe its gravitational effects on the things we can see. It's like watching a child's swing move on its own. You can't see the wind, but you know it's there. One of the most powerful techniques is gravitational lensing. Einstein's theory of general relativity tells us that mass warps the fabric of space-time. When light from a distant galaxy travels past a massive object like a cluster of galaxies, its path is bent by this warping, much like light bending through a lens. By carefully measuring how the images of background galaxies are distorted, astronomers can create a detailed map of the mass causing the distortion. Time and again, these maps reveal a vast, massive scaffold of dark matter, a cosmic web, that is far more extensive than the visible galaxies themselves. The glittering galaxies we see are merely where this dark matter has become most densely concentrated. As for what dark matter actually is, the leading theory points to a type of particle that doesn't interact with light or ordinary matter except through gravity. These WIMP, or weakly interacting massive particles, would be everywhere, streaming through you and everything around you right now, utterly undetectable without incredibly sensitive equipment. Countless experiments deep underground are searching for the faintest whisper of a collision between a dark matter particle and an atomic nucleus, but so far, the particles themselves remain elusive. And if that wasn't mysterious enough, in the late 1990s, astronomers made an even more startling discovery. Not only is the universe expanding, but that expansion is accelerating, pushed apart by a repulsive force now called dark energy. This was found by observing distant supernovae, which appeared dimmer than expected, meaning they were farther away than our models predicted. This force, making up about 68% of the universe, acts in direct opposition to gravity. While dark matter pulls the universe together, dark energy is pushing it apart. The leading explanation is that it's a property of space itself, a cosmological constant that Einstein once proposed and then discarded as his greatest blunder, which may turn out to have been one of his greatest insights. The grand takeaway is that our entire understanding of physics is built upon the visible 5%. The rest, the dark universe, is a profound mystery, a challenge to our fundamental models. It tells us that we are not just ignorant of some details. We are likely missing entire chapters in the book of how the cosmos works. Every time we gaze at the starry night sky, we are looking at a mere fraction of what's actually out there. A ghostly universe of dark matter and dark energy holding the stage together while the visible actors play their part in the light. And just when you thought volcanoes couldn't get any more dramatic, the solar system reveals an even more spectacular and bizarre form of eruption. Far from the fiery, lava-spewing mountains we know on Earth, there exists a completely different kind of volcano on the frozen moons of the outer solar system. This process is called cryovolcanism, cryo meaning cold, and it involves the eruption of water, ammonia, methane, or other volatiles instead of molten rock. These aren't mountains of fire and brimstone, but instead, geysers of ice and slush that blast forth from a world frozen solid on the surface, yet tantalizingly warm and liquid beneath its icy shell. The most stunning example of this is Enceladus, a small, bright moon of Saturn that looks like a perfect, shimmering ball of ice. For years, it was considered just another frozen rock, too small to have any internal heat. That all changed when the Cassini spacecraft arrived at Saturn and turned its instruments toward this unassuming moon. The probe discovered something that completely rewrote the book on planetary science. Massive plumes of water vapor and ice crystals erupting from a series of giant fissures near its south pole, jettisoning material hundreds of miles into space. Cassini didn't just photograph these plumes, it famously flew right through them, its sensors tasting the composition of the spray. The analysis was breathtaking. The plumes were not just simple water. They contained a surprising mix of organic compounds, including carbon, nitrogen, and oxygen-bearing molecules, the very ingredients necessary for life as we know it. So what could possibly power these spectacular frozen fountains on a world so far from the sun's warmth? The answer lies in a powerful and relentless gravitational tug of war. Enceladus orbits Saturn in a slightly elliptical, non-circular path. This means its distance from the giant planet is constantly changing. As it moves, Saturn's immense gravity squeezes and flexes the moon's interior, a process known as tidal heating. This constant kneading generates enough internal friction to melt a vast reservoir of water beneath the icy crust, creating a global subsurface ocean. The pressure from this buried sea eventually finds weak points in the icy shell, forcing a mixture of water, ice, and organic materials out into the vacuum of space through those famous tiger stripe fractures. Enceladus is not alone in this phenomenon. Jupiter's moon Europa is another prime candidate for cryovolcanism. Slightly larger than Enceladus, Europa is also thought to harbor a vast, global subsurface ocean locked beneath a thick, craggy shell of ice. While we haven't directly observed active plumes on Europa as definitively as on Enceladus, the Hubble Space Telescope has detected promising hints of water vapor venting from its surface. The upcoming Europa Clipper mission is designed specifically to hunt for these plumes and study the composition of this hidden ocean, which many scientists believe represents one of the most promising places to look for extraterrestrial life in our entire solar system. The implications of these icy volcanoes are nothing short of revolutionary for astrobiology. They provide a natural sampling mechanism. We don't need to drill through miles of ice to see what's in these alien oceans. The volcanoes are doing the work for us, ejecting the ocean's contents into space where a passing spacecraft can analyze it. The discovery of complex organic molecules in the Enceladus plumes suggests that beneath the ice, the necessary chemistry for life is not only present but potentially active. These subsurface oceans, kept liquid by tidal forces and shielded from harmful radiation by a thick roof of ice, could be the perfect incubators for microbial life, or perhaps even something more complex. These aren't just cold, dead worlds. They are dynamic, active, and incredibly exciting destinations that have fundamentally changed our understanding of where life might thrive. If the dynamic geology of Enceladus shows us that even frozen moons are worlds of change, then our next fact forces us to question the one constant we thought we could always rely on: time itself. The astonishing reality is that time does not pass at the same rate everywhere in the universe. Your clock on Earth ticks at a subtly different speed than a clock on the Moon, or on a satellite, or near a black hole. This isn't a malfunction of the clocks. It is a fundamental property of the cosmos, predicted by Albert Einstein's theory of general relativity over a century ago. and it's a phenomenon known as gravitational time dilation. To grasp this mind-bending concept, we have to let go of the idea of time as a universal metronome, ticking away at the same speed for everyone, everywhere. Instead, Einstein proposed that space and time are woven together into a single fabric called spacetime, and that gravity is not a force in the traditional sense, but rather a warp or curvature in this spacetime caused by mass. Imagine spacetime as a vast, stretchy trampoline. Place a heavy bowling ball in the center, and it creates a deep dimple. Now, roll a marble near the edge of that dimple. Its path will curve around the bowling ball. This is how gravity works. Mass tells spacetime how to curve, and curved spacetime tells mass how to move. But this curvature also affects time. The closer a clock is to a source of gravity, the deeper it sits within that gravitational dimple, the slower time will pass for it compared to a clock that is farther away. This means that time actually runs slower on the surface of the Earth than it does for a satellite in orbit. The difference is incredibly small, but it is measurable, and crucially, it has real-world consequences that we rely on every single day. The Global Positioning System, or GPS, is a perfect example. The network of 24 or so satellites that make up the GPS constellation are each carrying incredibly precise atomic clocks. According to general relativity, because they are farther from Earth's gravitational pull, their clocks should run faster by about 45 millionths of a second per day. But there's another relativistic effect at play: special relativity. Because the satellites are moving at about 8,700 miles per hour relative to observers on the ground, their clocks should run slower by about 7 millionths of a second per day. These two effects oppose each other, but the gravitational effect is stronger. The net result is that the clocks on the satellites gain about 38 millionths of a second each day compared to clocks on the ground. Now, 38 millionths of a second might sound negligible, but in the world of GPS, where timing is everything, it would cause catastrophic errors almost immediately. GPS works by triangulating your position based on the precise time it takes for a signal to travel from multiple satellites to your receiver. Light, and therefore radio signals, travel at over 186,000 miles per second. In just 1 millionth of a second, a light signal travels about 1,000 feet. If the satellite clocks weren't corrected for relativistic effects, the entire system would accumulate errors of over 6 miles per day, rendering it useless for navigation in a matter of minutes. So, the engineers who designed the GPS system had to purposely build a correction into the satellite's clocks. Before launch, the atomic clocks are adjusted to run slightly slower than their desired frequency, so that once they are in orbit and experiencing the combined effects of relativity, they will tick at exactly the right rate to synchronize with clocks on Earth. Your ability to get directions to the nearest coffee shop is direct, daily proof that Einstein's theories are correct. This prediction has also been verified by some of the most precise experiments in all of science. In one famous 1971 test, physicists J.C. Haefel and Richard Keating flew incredibly precise atomic clocks aboard commercial airliners around the world. After comparing the clocks that had flown with others that had remained on the ground, they found a discrepancy that matched the predictions of relativity. The flying clocks, experiencing slightly less gravity, had gained a few hundred billionths of a second. More recently, scientists have measured time dilation over a difference in height of just 1 foot. Two clocks, one placed on a table and the other on the floor, will tick at minutely different rates because the clock on the floor is a tiny bit deeper within Earth's gravitational field. The implications of this are staggering. It means that if you could stand on the surface of a neutron star, where gravity is billions of times stronger than on Earth, time would crawl for you. To an outside observer, your movements would appear to be in ultra-slow motion. Conversely, if you could venture into the empty void between galaxies, far from any significant mass, you would age more rapidly relative to everyone else. Your experience of time is not absolute. It is intimately and inextricably linked to your position in the gravitational field of the universe. Time is not a backdrop against which the universe plays out. It is a dynamic player in the cosmic dance, shaped and stretched by the matter and energy within it. Yet if you thought the icy geysers of Enceladus or the metallic snow of Venus were extreme, prepare to visit a world where the weather is not just hostile, but literally shatters all earthly conception of a storm. About 63 light-years from Earth, in the constellation Vulpecula, orbits an exoplanet called HD 189,733b. This cobalt blue world, which at first glance might remind you of our own serene Earth, is in reality a terrifying hellscape, a place where the atmosphere itself is a weapon. Here, winds scream across the planet at a staggering 5,400 miles per hour, and the rain is made of molten glass that falls sideways in blistering, horizontal sheets. The first clue to this planet's violent nature is its relationship with its star. HD 189,733b is a quintessential hot Jupiter, a gas giant that orbits terrifyingly close to its parent star. It is locked in a gravitational embrace so tight that a full year on this world, one complete orbit, takes just 2.2 Earth days. This extreme proximity means the planet is tidally locked, with one hemisphere permanently facing the scorching star and the other trapped in eternal night. The dayside temperature soars to a monstrous 1,700 degrees Celsius, hot enough to melt rock and vaporize metal. It is this incredible heat gradient, the drastic difference between the searing dayside and the cooler nightside, that fuels the planet's supersonic winds. The atmosphere, desperately trying to redistribute this immense thermal energy, screams from the hot side to the cold side at speeds that are nearly 7 times the speed of sound. On Earth, the fastest winds ever recorded during a tornado might reach 300 miles per hour. The winds on HD 189,733b are 18 times stronger, a continuous, planetary-scale hurricane with no end. But the true horror of this world isn't just the wind, it's what the wind carries. Astronomers using the Hubble Space Telescope performed a remarkable feat of remote sensing called spectroscopy on the light filtering through the planet's atmosphere. By dissecting that light into a spectrum, they found the unmistakable chemical fingerprint of silicate particles, tiny grains of what is essentially sand. On Earth, we heat sand to make glass. On HD 189,733b, the atmosphere does it naturally. The silicate particles, condensing in the slightly cooler upper atmosphere on the planet's night side, form into droplets of molten glass. These droplets are then caught by the unimaginable winds and hurled sideways across the sky at hypersonic speeds. This isn't a gentle rain, it's a relentless, abrasive sandblasting of molten glass across the entire planet. Any hypothetical spacecraft attempting to enter this atmosphere would be instantly stripped and scoured into nothingness. Visualizing such an alien environment is a challenge that pushes the limits of scientific art. Renderings of HD 189,733b, based on the data, depict a world of deep, brilliant blue, a color not from oceans, but from the scattering of light through a hazy atmosphere saturated with those silicate particles. The parent star, a fiery red dwarf, hangs large and menacing in a perpetual fixed position in the sky. The surface, if there is a solid one deep beneath the clouds, would be invisible, obscured by a violent, churning blanket of blue haze. And streaking through this haze, artist illustrations show these lines of glowing, incandescent material. The sideways rain of glass, illuminated from behind by the relentless star. It is a vision of both breathtaking beauty and utter violence, a planet that presents a serene, sapphire face to the distant observer, while hiding a cataclysm of fury within. This world stands as a powerful testament to the astonishing diversity of planetary environments. proving that the universe is capable of crafting beauty and terror in equal, spectacular measure. While the planet HD 189,733b presents a vision of cosmic violence on a planetary scale, the universe orchestrates collisions of an almost unimaginably larger magnitude. In a discovery that fundamentally reshapes our understanding of our place in the cosmos, we now know that our entire galaxy, the Milky Way, is not an island universe drifting in eternal solitude. It is, in fact, on an inescapable collision course with our nearest major galactic neighbor, the Andromeda Galaxy. In approximately 4 billion years, these two titans of the local universe will begin a slow-motion merger, a cosmic dance that will utterly transform the night sky for any life that remains on Earth. The very idea of two galaxies colliding conjures images of catastrophic stellar explosions and planetary chaos. But the reality is both more subtle and far more fascinating. A galaxy, for all its hundreds of billions of stars, is overwhelmingly composed of empty space. The average distance between stars is so vast that when galaxies interact, it is not a bumper car crash of suns and planets. Instead, it is the immense gravitational fields of the two galaxies that primarily interact, weaving together like two ghostly hands clasping. The stars themselves will mostly pass right by one another, their chances of a direct impact astronomically low. The real drama unfolds within the structure of the galaxies themselves. As they make their first close pass, their mutual gravity will begin to shred and distort their beautiful spiral arms, stretching them out into long, luminous tidal tails of stars and gas that are flung far out into intergalactic space. This isn't just theoretical. We can see this process happening elsewhere in the universe. Telescopes like Hubble have captured stunning images of other interacting galaxies, such as the Antennae galaxies, which show these spectacular tidal tails in exquisite detail. These observations provide a blueprint for our own future. Using the incredibly precise data on the motions of Andromeda and the Milky Way from the Hubble Space Telescope, scientists have created sophisticated computer simulations of the impending collision. These visualizations show the two galaxies first swinging past each other, then being pulled back together by gravity for a second, closer pass, and finally, over the course of another 2 billion years, merging completely. The result will not be two spirals, but a single giant ellipsoidal galaxy, a sort of cosmic blob that astronomers call an elliptical galaxy. For a time, it was jokingly nicknamed Milkdromeda, a portmanteau of the two original names. For a hypothetical observer on a future Earth, the changes in the night sky would be the most dramatic show in the history of the planet. As the Andromeda Galaxy, which is currently a faint, smudgy patch of light visible in dark skies, draws nearer, it would grow from a fuzzy blob into a breathtaking celestial presence. In the 3 to 4 billion years leading up to the first close encounter, Andromeda would swell to dominate the heavens. Eventually, it would fill a large portion of the night sky, its spiral structure becoming as clear and detailed as a photograph. During the first close pass, the sky would become a maelstrom of stars, with the familiar band of the Milky Way becoming warped and distorted as its stars are pulled outward by Andromeda's gravity. The core of the merger process would be a brilliant, chaotic display of light, with new stars flaring to life in compressed clouds of gas and dust. While our solar system will likely be flung into a much wider orbit within the new combined galaxy, the Sun itself is expected to survive the tumult, continuing to shine on a world that, by then, may be long since changed beyond recognition. This grand cosmic event reframes our existence from one of permanence to one of constant, majestic change. The galaxies we see as fixed landmarks are actually in a slow, gravitational ballet, with collisions and mergers being a fundamental part of a galaxy's evolution and growth. Our own Milky Way is a product of such ancient mergers, having consumed smaller dwarf galaxies throughout its history. The impending collision with Andromeda is not an apocalyptic end, but rather a new chapter in the life story of our galaxy, a transformation that will create a new, larger galactic home for the stars and planets that remain. It's a humbling reminder that even the mightiest structures in the universe are transient on these grandest of timescales, forever moving, merging, and evolving in the great expansion. While the galactic collision with Andromeda is a distant event on a billion-year timescale, we are protected from a far more immediate and constant cosmic barrage every single day. Our planet is enveloped in a powerful, invisible force field, the magnetosphere, a dynamic bubble of magnetism that shields all life on Earth from the sun's relentless fury. Without this protective barrier, our atmosphere would have been stripped away eons ago, and the surface would be bathed in lethal radiation, rendering the world a barren desert much like Mars. This magnetic shield is our planet's first and most important line of defense against the hazards of space. The sun is not just a placid ball of light. It is a raging nuclear furnace that constantly exhales a supersonic stream of charged particles, a solar wind. This wind, composed mostly of electrons and protons, races toward Earth at over 1,000,000 miles per hour. When these charged particles approach our world, they encounter Earth's magnetic field, which acts like a cosmic diversion shield. The field lines, which emerge from the South Pole and arc around the planet to enter at the North Pole, catch these particles and funnel them away from the surface, guiding them toward the poles in a spectacular celestial dance. The vast majority of this damaging radiation is deflected harmlessly into space, safeguarding our atmosphere and every living thing beneath it. Some of these trapped particles don't escape entirely. They become captured within two gigantic, donut-shaped regions encircling Earth known as the Van Allen radiation belts. Named after their discoverer, James Van Allen, these belts are zones of intense radiation where charged particles spiral along the planet's magnetic field lines, bouncing back and forth between the North and South poles. The inner belt is relatively stable, filled with high-energy protons, while the outer belt, swollen with electrons, swells and contracts dramatically with the sun's activity. These regions are so hazardous that astronauts and satellites must carefully navigate through them or plan missions to avoid them altogether, as prolonged exposure could be fatal to humans and destructive to sensitive electronics. The most beautiful and visible manifestation of this protective process is the aurora. When particularly strong solar storms, known as coronal mass ejections, slam into the magnetosphere, they can overwhelm its defenses. The magnetic field stretches and contorts under the pressure, and some of the energized particles are accelerated down the field lines toward the polar regions. As these particles plunge into the upper atmosphere, they collide with oxygen and nitrogen atoms. These collisions transfer energy to the atmospheric gases, exciting them. As the atoms return to their normal state, they release this energy in the form of light, creating the shimmering, dancing curtains of green, red, and purple that we know as the Northern and Southern Lights. This breathtaking light show is more than just a natural wonder. It is the visual evidence of our planet's magnetic field doing its job, a luminous sign that we are being protected from a storm of cosmic particles. To visualize this interaction, imagine a river of solar wind flowing around a rock. Our magnetic field is that rock, creating a teardrop-shaped bubble in the solar flow with a long magnetic tail stretching far away from the sun, much like the wake behind a boat. Satellite imagery and scientific visualizations show this constant pressure warping the field on the sun-facing side and stretching it into a 1,000,000-mile-long tail on the night side. If we could see this magnetic architecture with our own eyes, it would be the most prominent feature of our planet from space, a vast, shimmering cocoon of force that has, for billions of years, provided the safe haven necessary for life to not just begin, but to thrive and evolve into the complex world we know today. But if our magnetic field creates a silent, invisible shield, the universe also holds objects that create music on a scale so grand it defies human hearing. We've established that space itself is a vacuum, a silent medium, but that doesn't mean the objects within it are quiet. In one of the most astonishing discoveries of modern astronomy, we've learned that black holes, those ultimate symbols of cosmic silence and oblivion, can actually sing. Or more precisely, they can generate the deepest, most resonant notes in the entire universe. A hum so low that it takes a galaxy-sized instrument to detect it. This incredible phenomenon was discovered in the Perseus cluster, a massive group of galaxies about 250 million light-years away. At the heart of this cluster lies a supermassive black hole, billions of times the mass of our Sun, actively feeding on the surrounding gas. As this material spirals into the black hole's insatiable gravity, it doesn't go quietly. It unleashes titanic bursts of energy in the form of powerful jets that shoot out from its poles, plowing into the superheated gas that fills the space between the galaxies in the cluster. These jets act like a colossal piston, punching into the gas and creating immense ripples, pressure waves, that propagate outward through the cluster. These are not sound waves as we know them, since they're moving through a much thinner medium than air, but they are analogous to sound waves in their behavior. They are literal waves of pressure moving through a fluid, and they have a specific frequency. When astronomers pointed NASA Chandra X-ray Observatory at the Perseus cluster, they didn't hear anything. Instead, they saw these ripples. The observatory's X-ray vision revealed a stunning pattern of concentric rings in the multimillion-degree gas surrounding the black hole, like the ripples from a stone dropped in a pond, but on a galactic scale. By carefully analyzing the spacing between these ripples, scientists could calculate their wavelength, and from that, determine their frequency. The result was almost incomprehensible. The note being produced is a B-flat, but it is 57 octaves below middle C. To grasp how low that is, consider that a piano only covers about 7 octaves. The deepest note a human can hear is about 20 octaves above this black hole's hum. This note has a period, or oscillation, of about 10 million years. It would take 10 million years for a single wave to pass by a given point. This isn't just a low note. It's the deepest note ever detected in nature, a bass note resonating across 250 million light-years of space. Of course, we can't hear a note with a 10 million-year wavelength. To make this cosmic phenomenon accessible, scientists used a process called sonification. They took the actual frequency data from the Chandra observations and mathematically transposed it upward by 57 octaves, raising its pitch into the range of human hearing. What we get is not a melody, but a haunting, deep, and ominous hum. It's a sound that feels primordial and powerful, a fitting audio signature for an object of such immense gravity and mystery. This sonification transforms an abstract astronomical observation into a visceral experience, allowing us to hear the activity of a black hole for the very first time. It's a hum that speaks to the vast energies at play, a deep thrumming that underscores the dynamic and surprisingly musical nature of even the most destructive forces in the cosmos. Yet if the deep hum of a black hole hints at the immense scales of cosmic energy, the sheer population of the universe is perhaps even more difficult to fathom. We often hear the comparison that there are more stars in the observable universe than grains of sand on all the beaches and deserts of Earth. At first, this statement seems like poetic exaggeration, but the mathematics behind it reveals a truth that is profoundly humbling. Let's break down these numbers to truly appreciate the scale of our cosmic home. First, consider our own celestial neighborhood, the Milky Way galaxy. Astronomers estimate it contains between 100 billion and 400 billion stars. That's a range so vast that even the lower estimate is a number our brains simply cannot visualize. To put just 100 billion in perspective, imagine counting one star every single second without stopping. It would take you over 3,100 years to finish counting the stars in our galaxy alone. And our galaxy is just one of countless others. Now, let's zoom out to the observable universe, the portion of the cosmos we can potentially see from Earth. Limited by the distance light has had time to travel since the Big Bang. Current estimates suggest there are somewhere between 100 billion and 200 billion galaxies within this observable sphere. And each of these galaxies contains, on average, a similar number of stars as our own Milky Way. When you multiply these numbers together, the result is an almost incomprehensible figure. Taking a conservative estimate of 100 billion galaxies, each with 100 billion stars, gives you 10,000 billion stars. That's a 1 followed by 22 zeros. Now, how does that compare to the grains of sand on our entire planet? Geologists estimate that Earth holds roughly 7.5 times 10 to the 18th power grains of sand. That is 7 quintillion, 500 quadrillion grains. It's a number so large it feels abstract, yet it is dwarfed by the stellar census. When you place these two estimates side by side, the number of stars in the observable universe is at least several thousand times greater than the number of grains of sand on Earth. The comparison holds, and it is a staggering realization that the cosmos is filled with more suns than our entire world has grains of sand. But how do astronomers even begin to calculate such mind-numbing figures? They don't count every star or galaxy individually, of course. The process is a brilliant combination of direct sampling and statistical estimation. For stars in our own galaxy, scientists use powerful telescopes to count the number of stars in a small, representative patch of the sky. They then extrapolate that density across the entire volume of the Milky Way, adjusting for the fact that stars are more densely packed in the galactic center than in the sparse outer reaches. For counting galaxies, the Hubble Space Telescope performed one of the most famous experiments, the Hubble Deep Field. By pointing its sensitive cameras at a seemingly empty patch of sky for days, it revealed a universe teeming with thousands of galaxies, each a sprawling island of stars. By repeating this in different directions, astronomers could calculate the average density of galaxies in the observable universe and multiply that by its vast volume. The ultimate takeaway from this exercise is a profound sense of scale. Our planet, with its countless grains of sand, feels immense to us, but it is a single tiny world orbiting a single average star, which is one of hundreds of billions in a single galaxy, which is itself one of hundreds of billions in the observable universe. This isn't meant to make us feel insignificant, but rather to expand our understanding of the magnificent canvas of existence. It suggests a universe of nearly limitless possibility, where the potential for other worlds, and perhaps even other forms of life, is not just possible, but statistically probable. Every time you stand on a beach and let sand run through your fingers, you are holding a tiny fraction of your world, while above you stretches a cosmos with more suns than you could ever hope to hold. But while our moon may appear as a silent, static orb from Earth, it is far from geologically dead. It actually experiences its own version of earthquakes, known as moonquakes. These seismic events were a complete mystery until the Apollo missions, when astronauts placed a network of highly sensitive seismometers on the lunar surface. These instruments recorded thousands of seismic events over an 8-year period, painting a startling picture of a world that is constantly, if subtly, shaking. Moonquakes are categorized into 4 distinct types, each with a different cause. The most common are the deep moonquakes, occurring about 700 kilometers below the surface. These are not caused by shifting tectonic plates, as Earth lacks any such activity. Instead, they are triggered by the same gravitational tug of war that is slowly pushing the moon away from us tidal forces. As the moon flexes under Earth's gravity, stress builds up and releases in these regular, faint tremors. Then there are the shallow, thermal moonquakes. These are a direct result of the moon's extreme temperature swings. After 2 weeks of relentless, sun-scorched daylight, the lunar surface can heat up to 260 degrees Fahrenheit. When the 2-week-long night falls, it plummets to 280 degrees below zero. This 600-degree temperature difference causes the brittle crust to contract and expand so violently that it actually cracks and pops, creating small seismic signals. The most dramatic events are those caused by meteorite impacts. When a large space rock slams into the Moon, the energy of the impact sends vibrations ringing through the entire lunar body like a bell. The Apollo seismometers even recorded the impact of the spent lunar module ascent stages and the third stages of the Saturn V rockets being deliberately crashed onto the surface to create known seismic sources for calibration. Finally, there are the rare but powerful shallow moonquakes that can register up to 5.5 on the Richter scale. Lasting for incredibly long periods, sometimes over 10 minutes, these events are the most puzzling. On Earth, a quake that strong might last for 30 seconds because our planet's waterlogged crust dampens the vibrations. The Moon's incredibly dry and fractured interior, however, acts like a perfect resonator, allowing seismic waves to bounce around for what feels like an eternity. The data from these quakes has been invaluable for planetary scientists, acting as a sort of ultrasound for the Moon. By analyzing how the different types of seismic waves traveled through the lunar interior, researchers were able to map its internal structure. We now know the Moon has a crust, a mantle, and even a small, partially molten core. This information is not just academic, it's crucial for planning future lunar bases. Understanding the frequency, location, and strength of these moonquakes will be essential for designing structures that can withstand this unique geological activity, ensuring that the next generation of lunar explorers can live and work safely on a world that is still very much alive beneath their feet. Just when we thought we had a handle on the largest structures in the cosmos, astronomers made a discovery that stretched our understanding of the universe to its very limits. The Hercules Corona Borealis Great Wall isn't just a large cluster of galaxies. It is the single largest known structure in the entire observable universe, a cosmic filament so immense that its sheer size seems to defy the fundamental principles of cosmology itself. Discovered in 2013 by a team analyzing data from gamma-ray bursts, this gargantuan wall stretches an almost inconceivable 10 billion light-years across. To comprehend that scale, remember that a single light-year is about 6 trillion miles. This means the structure is so vast that light, the fastest thing in the universe, would take 10 billion years to travel from one end to the other. Given that the universe itself is only about 13.8 billion years old, the existence of such a colossal formation presents a profound mystery. This behemoth wasn't found by pointing a telescope at a single point in the sky. Its discovery was a triumph of modern astronomical surveying and statistical analysis. The team, led by astronomer Istvan Horvath, was studying the distribution of gamma-ray bursts, the most powerful explosions in the universe, which mark the deaths of massive stars. Because these brilliant flashes are visible across enormous distances, they act as perfect beacons to map the large-scale structure of the cosmos. By plotting the locations of hundreds of these bursts in three-dimensional space, a pattern began to emerge. An astonishingly high concentration of them was located in the directions of the constellations Hercules and Corona Borealis, revealing an immense, dense wall of galaxies previously hidden from view. It was like noticing that a seemingly random scattering of buoys in an ocean were actually all clustered along the edge of a single, massive, submerged continent. The existence of this structure creates a significant challenge for cosmology, specifically for the cosmological principle. This is a fundamental assumption that underpins our entire understanding of the universe. It states that on a sufficiently large scale, the universe is homogeneous and isotropic, meaning it should look roughly the same in every direction and contain no giant, irregular structures. The principle suggests that the cosmic web of matter should be fairly evenly distributed when you zoom out far enough. like the froth on a latte appearing uniform from a distance. The Hercules Corona Borealis Great Wall blatantly contradicts this. A structure spanning nearly a third of the observable universe is anything but uniform. Its existence forces scientists to question whether our models of the universe's evolution are incomplete. Perhaps the universe is not as smooth as we thought, or maybe this wall is a rare statistical fluke, a cosmic coincidence on a scale we can barely fathom. Either way, it serves as a humbling reminder that our grasp of the cosmos is still evolving. Visualizing this structure is a task that pushes the boundaries of both science and art. Imagine a three-dimensional map of the universe, with our Milky Way galaxy as a tiny, insignificant dot. As you pull back, you see the local group of galaxies, then the Virgo supercluster, which itself contains thousands of galaxies. You continue to zoom out, past other vast walls and filaments of the cosmic web, until you see it. A sprawling, river-like concentration of galaxies, a tendril of light and matter so long it dwarfs everything else in the known universe. It isn't a solid wall but a dense network of galaxy clusters, dark matter, and gas, woven together by gravity into the largest single thread in the cosmic tapestry. This visualization isn't just for show. It is a crucial tool that allows astronomers to study the anatomy of this leviathan and ponder the forces that could have sculpted it in the infancy of the cosmos, forever altering our perception of how the universe is built. While the universe is home to stars that burn at millions of degrees, it also contains stellar objects so surprisingly cool that you could, in theory, reach out and touch them without being burned. These are the brown dwarfs, and the coldest among them, known as ultra-cool dwarfs, have surface temperatures that hover around a balmy 98 degrees Fahrenheit, the same as the human body. They are the true wallflowers of the cosmos, objects that blur the line between a planet and a star, embodying a cosmic paradox of immense size paired with a startling lack of heat. A brown dwarf is essentially a failed star. It forms in the same way as a star, from a collapsing cloud of gas and dust. However, it simply doesn't gather enough mass to ignite the sustained nuclear fusion that defines a true star. For a star like our Sun, the crushing weight and heat at its core become so intense that hydrogen atoms are forced together, fusing into helium and releasing the tremendous energy that makes the star shine. A brown dwarf, typically weighing between 13 and 80 times the mass of Jupiter, never reaches this critical threshold. Its core may get hot enough to briefly fuse a rare isotope of hydrogen called deuterium or even lithium, but these reactions are short-lived. After burning through this limited fuel in a cosmic flash, the brown dwarf simply cools down. It never Chinese letter IGNITES. It spends the rest of its immensely long life gradually radiating away its residual heat of formation, slowly fading like a dying ember over billions of years. The challenge with these objects is that they emit almost no visible light. To find them, astronomers must turn to the infrared part of the electromagnetic spectrum, where heat radiation is detected. Powerful space telescopes like NASA's Spitzer Space Telescope and the Wide Field Infrared Survey Explorer, or WISE, have been instrumental in hunting these dim giants. The WISE mission, in particular, has discovered hundreds of ultra-cool dwarfs relatively close to our solar system. Because they are so faint, they can only be spotted when they are our near neighbors within a few dozen light years. One of the most famous examples is WISE 0855-0714, a brown dwarf with a surface temperature somewhere between -54 and 9 degrees Fahrenheit. It is often cited as the coldest known brown dwarf, a frigid, solitary world drifting through space, colder than a winter day on Earth. Imagining the surface of such an object is a journey into the bizarre. While artistic renderings often depict them as Jupiter-like worlds with turbulent, banded clouds, their atmospheres are likely far more exotic. At these low temperatures, Theories suggest that their skies could be filled with clouds not of water vapor, but of hot sand or even molten iron droplets, condensing and raining down into the interior. There would be no sunrise as we know it. The brown dwarf produces its own faint, deep red or magenta glow, illuminating the cloud tops with a dim, perpetual twilight. If you were to stand on such a world, you would be standing on no solid surface at all, but rather sinking into a deep, dense atmosphere that gradually transitions into a liquid or solid core. The gravity would be crushing, and the sky above would be pitch black, as the brown dwarf's faint glow is insufficient to light up any atmospheric haze. It's a vision of a world that is both immense and eerily quiet, a failed sun shining with just the memory of its birth. The study of these cold stars is more than a cosmic curiosity. It helps us understand the very boundary between planets and stars, revealing the different paths a collapsing cloud of gas can take in populating the universe with a class of objects we are only just beginning to comprehend. But while we often imagine alien oceans hidden beneath the ice of distant moons as still, dark, and silent abysses, one of them is actively reaching out, offering us a sample. Far beyond the asteroid belt, orbiting the ringed giant Saturn, the small moon Enceladus is doing something extraordinary. It's not just harboring a secret sea. It's sending its contents shooting out into space, writing its secrets across the void in plumes of ice and vapor for anyone with the right tools to read. This tiny, gleaming world, only 300 miles across, has become one of the most compelling places in our entire solar system in the search for life beyond Earth. For a long time, Enceladus was written off as just another frozen, geologically dead ice ball. That perception shattered completely with the arrival of the Cassini spacecraft at Saturn in 2004. As Cassini began its detailed survey of Saturn's moons, it turned its instruments toward Enceladus and discovered something that stunned the scientific community. Streaming from the moon's south pole were enormous, vibrant plumes of water vapor and ice crystals, erupting from a series of deep fissures nicknamed tiger stripes for their distinctive appearance. These weren't faint, wispy jets. They were massive geysers, shooting material hundreds of miles into space, forming a huge cloud of fine ice particles that, in turn, feeds Saturn's fainty ring. Cassini didn't just observe these plumes from a distance. In a series of daring maneuvers, it flew directly through them, its onboard sensors tasting and analyzing their composition in real time. The data sent back was nothing short of revolutionary. The plumes were primarily water vapor, but they also contained a surprising cocktail of other ingredients: simple organic molecules like methane and carbon dioxide, and more complex carbon-bearing compounds. Most tantalizing of all, the spacecraft's cosmic dust analyzer detected tiny silica nanograins particles that, on Earth, are only formed in hot water interacting with rock. This was the crucial clue. These nanograins pointed unequivocally to the existence of a global liquid water ocean sandwiched between the moon's rocky core and its icy outer shell. The water in this ocean is warm, and it's interacting with a rocky seabed, a scenario that on Earth supports thriving ecosystems entirely independent of sunlight. The engine powering this incredible system is the relentless gravitational pull of Saturn. Enceladus follows a slightly elliptical orbit, which means its distance from the planet is constantly changing. This varying proximity causes Saturn's immense gravity to squeeze and flex the moon's interior, a process known as tidal heating. This friction generates enough internal warmth to keep that vast subsurface ocean in a liquid state, despite the frigid -330°F temperatures at the surface. The pressure from this heated ocean forces the water up through cracks in the icy crust, where it erupts into the vacuum of space, instantly freezing into a brilliant spray of ice. Some of this material falls back to the surface, giving Enceladus its brilliantly reflective, almost pure white appearance, while the rest escapes entirely, creating a perpetual, majestic fountain that sustains a ring around a planet. The implications for astrobiology are profound. Enceladus possesses all three of the key ingredients scientists believe are necessary for life as we know it: liquid water, a source of energy from hydrothermal activity, and a rich buffet of organic compounds. This makes its hidden ocean a prime potential habitat for microbial life. The beauty of Enceladus is that it provides free sample return. We don't need to land a spacecraft and drill through miles of ice to see what's in that ocean. The Moon is actively ejecting its contents into space for us to analyze. Future missions, already in the planning stages, aim to fly even more sophisticated instruments through these plumes, specifically designed to look for complex organic molecules and perhaps even signs of biological activity. This small, icy moon, with its spectacular icy geysers, has transformed from a footnote in Saturn's catalog of moons into a leading candidate for answering one of humanity's oldest questions: are we alone in the universe? But even as we marvel at the dynamic plumes of Enceladus, a far colder and more pervasive phenomenon blankets the entire cosmos, a silent echo of the universe's very first moment. Every cubic centimeter of space, no matter how seemingly empty, is filled with a faint, cold glow, the cosmic microwave background radiation. This is the universe's baseline temperature, a frigid -270 degrees Celsius, a mere 2.7 degrees above the absolute zero point where all molecular motion ceases. This isn't just background static. It is the oldest light in existence, the cooled and stretched afterglow of the Big Bang itself. And its accidental discovery is one of the greatest scientific detective stories of the 20th century. The story begins in 1964 with two radio astronomers, Arno Penzias and Robert Wilson, at Bell Labs in New Jersey. They were using a highly sensitive horn antenna originally built for satellite communication, but they were plagued by a persistent, mysterious noise. It was a faint, steady hiss that came from every direction in the sky and wouldn't go away. They meticulously checked their equipment, even famously evicting a pair of pigeons that had nested in the antenna and cleaning up their conductive droppings, which they nicknamed white dielectric material. Yet the noise remained. Puzzled, they eventually learned that a team of physicists at Princeton University, led by Robert Dick, had been actively searching for precisely this signal, a predicted remnant of the universe's hot, dense beginning. Penzias and Wilson had stumbled upon the smoking gun for the Big Bang theory without even knowing they were looking for it. Their persistent, unwanted noise was the echo of creation, and it earned them the Nobel Prize in Physics. So what exactly is this radiation? To understand it, we have to travel back in time over 13 billion years. In the immediate aftermath of the Big Bang, the universe was an unimaginably hot, dense soup of particles and energy. It was so dense that light couldn't travel freely. It would constantly scatter off the dense plasma of electrons and protons, like trying to see through a thick, blinding fog. About 380,000 years after the Big Bang, the universe had expanded and cooled enough for electrons and protons to combine into neutral hydrogen atoms. This event, known as recombination, suddenly cleared the fog. For the first time, light could travel unimpeded across the cosmos. That first flash of light, released when the universe was a searing 3,000 degrees Celsius, has been traveling ever since. But as the universe expanded, that light stretched along with it. The wavelengths grew longer, shifting from visible light to infrared, and eventually to microwaves, while its effective temperature dropped to just a few degrees above absolute zero. The cosmic microwave background is that same ancient light, now cooled and faded by the immense expansion of spacetime over billions of years. But this background is not perfectly uniform. While it is incredibly smooth, the most sensitive maps, like those from NASA's Wilkinson Microwave Anisotropy Probe and the Planck satellite, reveal tiny fluctuations, minute variations in temperature on the order of 1/100,000th of a degree. These fluctuations are the most important part of the story. They represent tiny density variations in the early universe, slightly hotter, denser spots and slightly cooler, emptier patches. In the hot, dense early universe, gravity began to work on these imperfections. The slightly denser regions had slightly stronger gravity, which pulled in more matter, growing denser still over billions of years. The slightly emptier regions lost matter to their denser neighbors. This gravitational amplification is what seeded the entire large-scale structure of the universe we see today. Those tiny temperature fluctuations were the blueprints for everything, the first gravitational seeds that would eventually grow into vast clusters and superclusters of galaxies, the very architecture of the cosmos. The cosmic microwave background is therefore far more than a cold relic. It is a detailed baby picture of the universe, a fossilized map of its initial conditions that allows us to test our most fundamental theories of cosmology and understand our own origins on the grandest possible scale. And if the cosmic microwave background is the universe's oldest photograph, revealing its infancy, the discovery of planets orbiting two stars brings science fiction thrillingly to life. Luke Skywalker's iconic double sunset on Tatooine in Star Wars was a tantalizing fantasy for decades. But we now know these circumbinary planets are not just a cinematic dream. They are a vibrant and surprisingly common reality in our galaxy. These worlds don't orbit a single star. They are locked in a delicate gravitational dance with a binary star system, creating skies with two suns and the potential for some of the most spectacular sunrises and sunsets imaginable. The very existence of these planets defied early expectations. Astronomers initially thought the gravitational tug-of-war between two stars would be far too chaotic and unstable for a planet to form or maintain a stable orbit. The complex, shifting gravity would likely tear apart the protoplanetary disk of gas and dust from which planets coalesce, or quickly fling any nascent world out into the void. Yet, nature found a way, and the key to stability lies in a specific orbital configuration. For a planet to survive in such a system, it must orbit far enough away from both stars that their gravitational influence merges into a single, stable point. The planet essentially treats the binary pair as a combined gravitational anchor, tracing a wide, looping path around the center of mass of the entire system. This keeps the planet safely away from the chaotic gravitational zone between the two stars, allowing it to enjoy a stable, if somewhat unusual, orbit. The undisputed champion in the hunt for these worlds was NASA's Kepler Space Telescope. Its primary mission was to detect planets by observing the tiny, periodic dimming of a star's light as a planet passed in front of it, an event known as a transit. In a binary system, this becomes infinitely more complex. The two stars are already regularly eclipsing each other from our viewpoint, creating a predictable pattern of brightness dips. Finding an additional, smaller dip from a planet required ingenious new data analysis techniques. Kepler's incredible precision allowed it to do just that, and its discoveries like Kepler 16b, Kepler 34b, and Kepler 35b confirmed that Tatooine was real. These pioneering finds opened the floodgates, and we now know of dozens of such planets, with many more candidates waiting for confirmation. Some even reside in the habitable zone of their binary systems, the region where temperatures might be just right for liquid water to exist on their surfaces. But the true wonder of these worlds is experienced from their surface. Imagine standing on a plane of Kepler 16b. Your two suns, one an orange star about 2/3 the mass of our Sun, and the other a smaller, cooler red dwarf, would trace intricate paths across the sky. Some days they would rise and set together, casting twin shadows that slowly merge and separate. On other days, one might rise hours before the other, creating an extended dawn. The colors during a double sunset would be a spectacle beyond anything on Earth. As the larger, orange star dipped below the horizon, it might paint the sky in deep reds and purples. Then, just as you thought the show was over, the smaller red sun, hanging higher in the sky, would begin its own descent, bathing the landscape in a completely different hue, perhaps a dim, eerie crimson. The light levels would fluctuate constantly, and the length of a day would be unpredictable, changing with the complex orbital dance of its twin suns. It's a dynamic, ever-changing celestial ballet that would make the simple rhythm of day and night on Earth feel placid by comparison. The discovery of these systems doesn't just add to our catalog of exoplanets. It profoundly expands our understanding of planetary formation, proving that planets can emerge and thrive in environments we once thought were too hostile. And it gives us a universe far more diverse and wonderfully strange than we ever dreamed. And if the dance of binary stars shows us the intricate choreography of planetary orbits, the grandest and most profound motion in the cosmos operates on a scale that challenges the very limits of physics. We arrive at a fact that seems to break the universe's ultimate speed limit. Space itself is expanding faster than the speed of light. This isn't a violation of Einstein's laws, but rather their most astounding consequence, a subtle distinction that reveals the true, bizarre nature of the cosmos. The rule that nothing can travel through space faster than light is one of the most famous tenets of physics. No information, no particle, no spaceship can exceed this cosmic speed limit. However, the fabric of spacetime itself operates under a different set of rules. There is no universal speed limit for the expansion of the arena. The stage upon which everything plays out can stretch and grow at any rate. Think of it like baking raisin bread. As the dough rises in the oven, the raisins which represent galaxies are carried apart from each other. No raisin is moving through the dough faster than any other, but the space between them is expanding. Now, imagine the oven is so powerful that two raisins on opposite ends of the loaf are being separated at a rate that, if you were to measure it, would be greater than the speed of light. The raisins aren't breaking any rules, the dough itself is doing all the work. This incredible expansion isn't just happening, it's accelerating. This is the work of the mysterious force we call dark energy. Imagine throwing a ball into the air. You'd expect gravity to slow it down, eventually bringing it back to Earth. Now, imagine you throw that ball and instead of slowing, it shoots upward faster and faster, as if repelled by some invisible, anti-gravity force. This is precisely what dark energy is doing to the universe. It's a repulsive force, woven into the very fabric of empty space, that is causing the expansion of the cosmos to speed up over time. The more space there is, the more dark energy there is, and the faster the expansion becomes. It's a runaway process with staggering implications for the far future of the universe. To visualize this, the balloon analogy is the most effective. Picture the surface of a partially inflated balloon with coins glued to it, representing galaxies. As you inflate the balloon, every coin moves away from every other coin. From the perspective of any single coin, all the others are receding. A coin on one side of the balloon sees a coin on the opposite side moving away the fastest, because there is more expanding balloon surface between them. Now, if you could inflate that balloon at an accelerating rate, those distant coins would eventually be moving apart at a relative velocity greater than the speed of light. The coins themselves are fixed to the balloon's surface. It is the rubber stretching between them that creates the immense distance. This has a profound and strangely melancholic effect on our observable universe. Because the most distant galaxies are being carried away by the expansion of space at speeds exceeding that of light, their light can no longer reach us. The photon leaving a galaxy, traveling at light speed toward us, is like a swimmer trying to cross a river that is flowing faster than they can swim. They make no headway against the current. Over billions of years, as the expansion accelerates, more and more galaxies will cross this cosmological horizon and disappear from our view. The light they emit today will never arrive at Earth. Future astronomers in the far, far future, if they exist in our galaxy, will look up into a much darker sky. They will see only the local group of galaxies, gravitationally bound to us, and beyond that, an impenetrable blackness, with no evidence of the grand cosmic web or the Big Bang. They might conclude the universe is static, small, and eternal, having lost all clues to the vibrant, expanding cosmos we see today. This accelerating expansion, driven by dark energy, is quietly and inexorably erasing the evidence of the universe's history. A constant reminder that our window to see the cosmos in all its glory is only open for a limited time. From the moon's slow retreat to the silent, screaming winds of a planet where it rains glass, our journey through the cosmos has revealed a universe far stranger and more magnificent than fiction could ever devise. We've stood in awe of a hexagon swirling at Saturn's pole, a perfect geometric wonder etched onto a gas giant by physics we are only beginning to grasp. We've explored the profound silence of the void, a silence so deep it amplifies the hum of our own sun, and the bass note of a supermassive black hole singing a note 57 octaves too low for us to hear. These revelations are more than just trivia. They are fundamental shifts in perspective. They teach us that time is not a constant river but a flexible stream, flowing at different rates depending on where you stand in the gravitational fabric of spacetime. They show us that water, the very essence of life, is one of the most abundant molecules in the universe, forged in the dark clouds between the stars and delivered to worlds like ours. And perhaps most humbling of all, they force us to confront the reality that everything we can see, every star and galaxy, accounts for a mere 5% of existence. The rest is a mystery of dark matter and dark energy, the universe's deepest and most compelling secrets. So much of what we thought we knew has been turned on its head. Planets made of diamond, moons spewing water into space from hidden oceans, and entire worlds wandering alone in the eternal night. Each discovery peels back a layer, only to reveal a new set of questions waiting beneath. This is the beautiful paradox of astronomy. The more we learn, the more we understand how much we have yet to discover. The universe is not a puzzle to be solved, but an endless frontier to be explored, a constant source of wonder that reminds us of our humble place in a grand, unfolding story. Now, we want to hear from you. Which of these facts completely rewired your brain? Was it the realization that your GPS relies on Einstein's theory of relativity to work? Or the haunting image of those eternal Apollo footprints on the moon? Share your most shocking moment in the comments below. We read every single one. If your curiosity for cosmic mysteries is still burning, you'll want to watch our next video, which explores the terrifying and fascinating science of black holes, from the event horizon to the singularity. And for more journeys to the furthest reaches of space and the deepest questions of existence, make sure to subscribe to the channel and hit the bell icon so you never miss an upload. The universe is vast, strange, and full of stories waiting to be told. We can't wait to explore them with you.